terms of linear classification, we are going to discuss two different models. One is LDA, or linear discriminant analysis, and the second one is logistic regression. Well, let's recall our earlier definition on learning types. So one of the learning types is supervised learning. So you have data set from index number 1 to large n, and small n is the index variable. So small dn means single data instance, and each of them come in pair. So x is usually input, y is usually output. Given that we have talked about regression problem where y is continuous, and we are moving on to new problem. So that is classification. Here y is discrete. So where we looked at this slide over and over, classification is where you are given a email message where you want to identify it is either spam or a regular message. You can also collect a property of a fruit, and based on your collection of the information, you can try to learn a single method that identifies where based on the property of a new fruit where you want to identify it is either orange or apple. Well, speaking of classification, well, there is a core part of the decision that is a discriminant function. So a common way to represent a classifier is using a discriminant function. So it is making decision. Well, first of all, we can think of where you have k plus 1 classes. That means you have k plus 1 functions. Each of them represent each class. And this function, what it does is maximize the output when it sees the data instance that fall in the same class. And usually we are dealing with binary classification, but it can be also multi-class like described here. So when it is binary, your C is simply either 0 or 1. Well, given that discriminant function is written as this, so where discriminant function GCX, that is maximizing C given input X, where C is deciding the class ID of instance X. So well, this simple formula is representing the decision rule in classification. Well, given that, we can think of binary classification in this way. So you have given two different functions, each of them representing the class number 0 and class number 1. And each of them takes the input instance and outputs some value. When the output of G1 is larger than G0, then it's going to be class 1. On the other hand, if G1 is smaller than G0, then the data fall in that region is class 0. Indeed, we don't need this equality here, so we only need the inequality. And where those two functions meet, so if we try to identify the point where the output of G1 and G0 are identical, where you can draw this green line. And this area where you cannot really make a fixed decision, so here you need a tie break. On the other hand, where based on this green line, you can make a decision. So this is often called as decision boundary. So the whole purpose of machine learning, especially in classification, where virtually the ultimate goal is to find out a line that corresponds to the decision boundary given your data. Given that there are two types of classifier, so one type is a generative classifier, the other is a discriminative classifier. So the first class, generative classifier, well, it is sort of based on the Bayesian theorem. So where earlier we formulated the Bayesian theorem. So given this function, we can try to by x, y. The numerator of the right-hand side is indeed equivalent to the joint distribution. So this is a joint probability of x and y given parameter theta. The ultimate goal in generative classifier is to model the joint probability of your input and output. So what you're testing in this class of classifier, where you have input X and you are pairing your data instance with one of the class that you have and estimate the probability. So this is number one. And next time you want to plug in your data instance with another class that you have and try to estimate the probability. And after that, you want to make a decision based on the quantity that you estimated. So if the first one is larger, then your decision is 1. If the second one is larger, your decision is 0. And well, one of the common problem with joint probability, where the search space of estimating joint probability is quite large. So in order to make this computation possible, we are decomposing the joint probability in this way. So well, to summarize, in generative classifier, the goal is to model the joint probability of input and output. But modeling input and output directly is difficult. So using Bayes' theorem, we often decompose things in this way. And one of the common example is linear discriminant analysis that we are going to discuss today. And later on, we are going to see naive-Bayes model. The name generative classifier is coming from your classifier can be used to generate a new sample. This is just a side note. On the other hand, there is another class of classifier that is discriminative. So in order to make a decision, you eventually want to have this conditional probability. So this is the probability of y, your class label, given your input, parameterized by zeta. So well, eventually generative classifier try to do the same. So in both cases, we need to estimate this conditional probability, y given x, here y given x. But how to achieve it is different. So in generative classifier, you initially try to model the joint probability. So from joint probability, you want to recover this decision function. In discriminative classifier, on the other hand, we want to directly model this conditional probability. So well, things are quite vague at this point, I believe. So let's try to find out the meaning.